Hello everyone. Today we're going to take another look at relative extrema, and we're specifically going to focus on some different functions and just practice finding the relative max and mins for those different types of functions, as well as intervals of increase and decrease. So here we go. Okay, so the first types of functions that we're going to take a look at are absolute value functions. And so the one thing I really want to make sure that you remember and take note of for these is that for absolute value we're going to kind of deviate from the rules that we've set up in the previous video. And for absolute value functions, I want you to remember that we must make a sketch. Okay, so that's actually what we're going to do instead of finding the derivative. We're going to actually look at the sketch of this. So if we take a look at, if we remember our absolute value function, the original, okay, we know that it looks right like this. Okay, now we want to take into account the transformations that occurred here and apply them. Okay, so the first thing we notice is that it's negative, and so that means it's going to be downward facing. Okay, inside the parentheses we have a -4, which tells us we're going to have a shift right 4. Okay, and then also outside of the parentheses we have a -2, which tells us we're going to go down 2. All right, so if we just kind of take a look at what that's going to look like, all right, so we are going to go upside down. We're going to go to the right 4. So 1, 2, 3, 4 to the right and down 2. And that's going to be our vertex, and it's going to be a downward facing absolute value function. Okay, once we have that graph sketched, then we can ask ourselves, we can take a look at that graph and ask, where are our critical points? Okay, and remember, critical points are when the derivative, okay, so when the derivative equals 0 or the derivative does not exist. Okay, so if we take a look at this, where would the slope of this graph either equal 0 or not exist? And hopefully you can see that that would happen, a critical point at x is equal to 4. Okay, that here on our graph would be our critical point, because it comes to a point, so it would not exist. Okay, the slope would not exist. So from that now, I can go ahead and make my number line. So I can put 4 here, and I'm going to show that it doesn't exist at 4. Remember, I always put my labels. Okay, so I don't have the equation for the derivative to test values to the left and to the right of the 4, but I do have the graph. And so I can look to see numbers to the left of 4, what is happening with the slope? Well, the slope is definitely positive to the left of 4, and so we had a increasing function. And to the right of 4, you can see that the slopes are negative, and so we had a decreasing function. Okay, so I'm now ready to make some conclusions. So I should be able to say that f is increasing from -infinity to 4. And why? Because f prime of x is greater than 0. I can also say that f is decreasing, oops, I missed a c there, from 4 to infinity, because f prime of x is less than 0, is negative. And lastly, I can say that I have a relative max at x equals 4, because f prime of x changes from positive to negative. All right, let's take a look at the next one. Okay, so our second example, we have another absolute value function, and again, remember we're going to, because it's an absolute value function, we are going to go ahead and take a look at the sketch of this. All right, so this is definitely not one that you probably have practiced before, but I want you to understand here that you are going to just take the absolute value of a quadratic function. So the way that we sketch this is we say, what, first of all, would x squared minus 16 look like? So we know x squared function, okay, is obviously a parabola, and x squared would have its vertex at the origin. And so what happens when we have that minus 16 is it goes down 16, okay? And so that means I know that it's going to cross through the y-axis here at negative 16. Okay, I also can tell that my zeros would be when x was equal to negative 4 or positive 4. And so I have a parabola that looks like this. Okay, so if that's my parabola for x squared minus 16, what would x squared, the absolute value of x squared minus 16, look like? Well, let's keep in mind that absolute value just makes it positive, okay? And so these values that are already positive would remain. So those values are still on our graph. But what happens to this part of the graph that right now is underneath the x-axis that are negative values? Well, all that's going to happen for that is they're going to flip up. So instead of crossing at negative 16, it's now going to cross at positive 16. And you literally have a graph that kind of does this. Okay? And so you just took that that part of the graph that went below the x-axis and you flipped it up. Okay, so now that we have a sketch of the graph, and obviously the one in red is our absolute value of f of x squared minus 16. Now that we have that sketch, we should again ask ourselves, are there any critical points? Okay, so are there any critical points? Well, I can say that there is a critical point at x equals 0, because that's where the derivative is equal to 0, right? So when I look at 0, I can tell that I am going from increasing to decreasing, and that it is not forming a point or a cusp of any kind, that it is a nice smooth curve there, and so that in fact would have a horizontal tangent, and so that would be a slope of 0. I can also see that I'm going to have two other critical points that I'm going to have at x equals negative 4 and at 4. And that's not because the slope is equal to 0, but here I would say that f prime of x does not exist. And again, why is that? Well, for those points you can tell because we had to very abruptly take and flip it up, okay, then it formed these points here. Okay, and so because of that, it came to a point, and so therefore the slope does not exist. You would not be able to draw a horizontal tangent. Your tangent line would kind of teeter at that place. All right, so now we have these three critical values, so we're ready to kind of put those on a number line. We have negative 4, 0, and 4. And so we're ready to kind of label what's going on. So these two does not exist, and this is our 0. All right, so to the left of negative 4, what would we say about the graph? We'd say that the slope was decreasing, so negative, and that meant you had a downward facing curve. Okay, in between negative 4 and 0, you can see the slope is now increasing, and so it's going up. From 0 to 4, the slope was again decreasing, going down, and from 4 up beyond, there was a positive slope, so the graph was increasing. Okay, so we have that now, and we should be able to write some conclusions about the graph of f. Okay, so we should be able to conclude that in fact f is increasing over the interval. So we can say negative 4 to 0, and also from 4 to infinity. And again, that would be because f prime of x is greater than 0, is positive. F is decreasing between negative infinity up until negative 4, and from 0 to 4. And the reason for that, the justification, is that f prime of x is less than 0, is negative. Okay, we should be able to say that we have two relative mins, so relative minimums at x equals negative 4 and x equals 4. Okay, and you can see that down here because it's coming down and then back up, down and then back up. So at 4 and at negative 4, we have our relative mins, and why? Because f prime of x changes from negative to positive. All right, we can then say our last conclusion that we have a relative max at x equals 0. And that would be the opposite reason, because f prime of x changes from negative to positive. Okay, so the big thing I want you to remember and take home is that this is the only function where I actually want you to sketch it, okay? Because taking the derivative of absolute value function is not something that we're going to do by hand. We're actually going to go ahead and take a look at the graph in order to evaluate that. So always remember, for absolute value functions, make a sketch of the graph and then you still need to make your number line in order to make your conclusions. This is your part of your work, part of your justification for these conclusions that you have. All right, now let's move on to other functions. Okay, so we're going to take a look at this rational function, f of x equals x cubed divided by x squared minus 3. So hopefully you recognize that we cannot split this because we have a binomial in the denominator. And so in order to take the derivative of this function, which is of course what we need to do in order to find our critical values, we're going to have to use the quotient rule. So we would say f prime of x is equal to low, so x squared minus 3, d high, so 3x squared, minus high, x to the third. D low would be 2x, that's it, 2x, all over low squared, so x squared minus 3 squared. Okay, so if I just kind of clean up the top for a second, let's see here. This would be 3x to the fourth minus 9x squared. Of course, I'm distributing a negative x cubed. It's actually just to that one term, so negative 2x to the fourth over x squared minus 3 squared. So one last step, f prime of x is just going to be x to the fourth minus 9x squared on top over x squared minus 3 squared. Okay, so that is our the derivative of f of x. Now remember, in order to find our critical values, we're always asking for two things. When does the derivative equal 0? And when is the derivative undefined? In order to get that answer, okay, for a rational function, we are going to look at both the numerator and the denominator. The numerator equal to 0 gives us our zeros. The denominator equal to 0 gives us our undefined values. Okay, and we need both of those in order to move forward. Okay, so I'm going to go ahead and first of all set my numerator, x to the fourth minus 9x squared equal to 0. Alright, so I'm going to go ahead and factor out that x squared, and I'd have x squared minus 9 equals 0. So two different things here. We're going to have x is equal to 0, and we're also going to have x is equal to positive and negative 3. Alright, so there's three critical values already. Alright, and now on to the denominator. So we have that x squared minus 3 squared equals 0. So remember, if we have basically this is just saying x squared minus 3 times x squared minus 3. So whatever we get, we just have to set the inside equal to 0. We don't have to worry about that squared at all. Alright, so it's just x squared is equal to 3. So x equals, again, positive or negative radical 3. All right, so we end up with 5 critical values for this one. Okay, so we're going to go ahead and set up our number line. So we have negative 3, negative square root 3, 0, square root 3, 3. All right, and above the 0 and negative and positive 3, I'm going to go ahead and put zeros. Above the negative root 3 and positive root 3, I'm going to put does not exist symbols. All right, and again, this is f prime, and this is f. All right, so now we need to test some values. All right, and remember, we're testing them back into f prime, and all we care about is if it's a positive or negative output. Okay. Okay, I do want us to take note of the denominator. And what I notice here is that the denominator of my derivative, it is a x squared minus 3 squared. So what does that tell us about the positive or negative value of the denominator. It tells us, hopefully you recognize, that it's always positive, that any number squared is going to end up with a positive in the denominator. So we know for each of these that really it's just whatever the numerator is going to give us our positive or negative value. Okay, so the first number we're going to go ahead and test is -4. So if we plug -4 in here, we'd have -4 to the fourth minus 9 times -4 squared. Well, I know that to the fourth and to the second is going to get rid of the negative, okay? So what do I know about 4 to the fourth compared to 9 times 4 squared? Well, certainly I know that 4 times 4 times 4 times 4 is a larger value than 9 times 4 times 4. And so I can definitely say that that's going to be a positive output. Okay, so now I need to test a value between -3 and -√3. So you might not know exactly what negative radical 3 is in order to make your test. Well, keep in mind that negative radical 3 would have to fall between negative radical 4 and negative radical 1. Okay, and so that would tell me that -2 would have to be to the left of negative√3, which of course is -2. Okay, so -2 to the fourth would be a positive 16. Okay, so 16 minus 9 times -2 squared, so 9 times 4 is 36. So this would be a negative. All right, in between negative radical 3 and 0 would be like a -1. So that would be 1 minus 9 times 1, which is again going to be negative. Okay, a value between 0 and radical 3 would be, again, like a radical 1 or 1, and the same thing is going to happen. You're going to have 1 minus 9, so you're going to get a negative. Same thing is going to happen for a positive 2 when we plug it in. We're going to get that 16 minus 36 again. And then when we plug in positive 4, okay, we need not know the value. We just know that 4 to the fourth is definitely bigger than 9 times 4 squared, and so you're going to have a positive. And so we have these negatives repeating itself over and over. So what does that mean about f, about the original function? It means that we are increasing, and then we're decreasing, 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 increasing. Okay, so you can see here that if you take a look at this, what the idea is here, right here we're going to go up and then come back down. So that would tell us at -3 we will have a relative max, and then we go down, 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 and then we come back up again. And so at +3 we're going to have a relative min. All right. Okay, so we're ready to make some conclusions here. We're ready to say that f is increasing between -infinity and -3, and from 3 to infinity. And that's because f prime of x is greater than 0. We're ready to say that f is decreasing. And we have to list all of these intervals kind of independently, all right? So we have to stop at the critical values in between. So we would say from from -3 to negative radical 3, union with negative radical 3 to 0, union with 0 to √3, and √3 to 3. Again, that would be because f prime of x, the derivative, is negative. All right, we said we had a relative maximum at x equals -3 and relative min at x equals 3. And I'm just going to say kind of for both of those, that's because f prime of x changed sign. So if this was actually the exam, of course I would write out that for the relative max it changed from positive to negative, for the relative min because f prime changed from negative to positive. Okay, the next function we're going to take a look at is a radical function. And once again, we're going to approach this exact same way. We want to go ahead and take the derivative of the function. So in order to do that, I actually want to probably rewrite f of x as 9 minus 3x squared to the 1/2. And so then I would say that this is 1/2, 9 minus 3x squared to the negative 1/2 times the derivative of the inside, which would be negative 6x. Okay, so if I kind of clean that up for a second, I would have f prime of x is equal to, well, half times negative 6 would be negative 3, and then of course my x is in the numerator, and in the denominator I would have that 9 minus 3x squared to the positive 1/2, or the square root of 9 minus 3x squared. Okay, so there's the derivative, and again, once I have the derivative, I need to consider two different things. Where does the numerator equal to 0? And where is the denominator equal to 0? Okay, so first of all, our numerator, that's a pretty easy one. That would just be x is equal to 0. So that's our first critical value. That is where we have a 0, okay, a slope of 0. Okay, for the second one, we're searching out for any undefined values, and that would be where the denominator equals 0. So I'm going to go ahead, and I know that the square root of 0 is 0, so I'm just going to take that 9 minus 3x squared and set that equal to 0. So I'd be looking at when 9 is equal to 3x squared. Divide by 3, I'd have 3 is equal to x squared, so x is equal to positive negative radical 3. Okay, so those are my three critical values. 2, making where the derivative is undefined, so undifferentiable, and 1, where you have a slope of 0. All right, so we're going to go ahead and make our number line so we can test our values. All right, so we need to put all of our critical values on our number line. So negative square root 3, 0, and square root 3. And of course, these are where it was undefined, and this is where you have a slope of 0. This is our f prime, this is f. So we're ready to begin testing some values. So I'm going to pick a value smaller than negative root 3, so I'll say negative 2. Okay, and I'm going to plug that into the top and bottom. So negative 3 times negative 2 would be a positive, divided by, well, 9 minus 3 times negative 2 squared would be 9 minus 3 times 4. So 9 minus 12, what happens there? You get a negative, but it's the square root of a negative. So what happens? We get imaginary. And since that is not positive or negative, we are actually going to not even consider this part of the number line. We really don't deal with imaginary complex numbers in calculus, and so when we get that imaginary, that's just going to be something we don't even consider on the graph. And we'll talk about why that is in a second. All right, so then if we look at the next part, a number between negative square root 3 and 0, so negative 1 would work. So negative 3 times negative 1 in the numerator would be positive, and on the bottom, 9 minus 3 times 1 would be a positive. The square root of a positive number is positive. So we end up with a positive there. All right, which means that we would have a increasing function f. All right, so between 0 and radical 3, we'll test a 1. So it's going to be a negative on the top, and 9 minus 3, again, is positive. Square root of a positive is positive. So, oops, we're going to end up with a negative, because negative divided by a positive is, of course, negative. So, decreasing graph for f. All right, and the last one, we'll go ahead and plug in a 2. So, negative 3 times 2 is, of course, negative. And then on the bottom, you again have that 9 minus 3 times 4. So 9 minus 12 is the square root of a negative, so we have imaginary, so this part of the graph doesn't exist, okay? And what that really means, that the graph doesn't exist, is literally if you were to graph the original function, there would not be anything graphed in the up until negative root 3 and after positive root 3. Okay, so that's what that means, because there is no real outputs there. And so that is why we kind of just X that part of the number line off. All right, so we're ready to go ahead and make our conclusions. I'm just going to do them verbally here, and you can make sure that you get them written down in your notes. All right, so I would say that the graph is increasing, the f is increasing from negative root 3 to 0, and that is because f prime of x is greater than 0. I would say that f is decreasing over the interval 0, 3, and that's because f prime of x is, of course, less than 0. And then I would say that what do I have here? Well, if I'm going up and then coming back down, I would definitely say that I have a relative maximum at x equals 0 because f prime changed from positive to negative. All right, so we have now done a radical function, a rational function, and an absolute value function. We have one left to do, and that's going to be our trigonometric function. All right, so I know that you are excited about this one. Let's get right into it. First thing I need to do is go ahead and take the derivative of f. All right, and so I have the derivative of 1/2 x is f 1/2, and the derivative of negative minus sine x is going to be minus cosine of x. All right, and so if you notice here, this is important that they do give us this interval that we are graphing the original function over, and that's going to become important as we solve, because we know, of course, that a trig function is periodic, so it repeats over and over. And so if they didn't give us this interval, there'd be no stop to my number line, all right? And so we want to make sure that we pay attention to that interval and use it throughout the problem. Okay, so the very first thing we need to do now is, of course, we know trig functions, it's not where they're undefined unless it's tangent, or if we're talking about one of the reciprocal functions, secant, cosecant, or cotangent. But the sine and cosine, we are not talking about undefined, we're just talking about where it equals 0. So we're going to go ahead and set this equal to 0. Okay, so probably the easiest way to solve this would just be to add the cosine over. So I have cosine x is equal to 1/2. All right, so now I'm kind of thinking about where does cos x equal 1/2? So of course, we should be thinking about our unit circle here, and we're thinking about what points on the unit circle give us an x value of positive 1/2. And this is over the whole unit circle, all the way from 0 to 2 pi. All right, so we should be aware that we are looking in quadrants 1 and also quadrants 4. Why are those two quadrants? Because that's where cosine is positive. All right, so in quadrant 1, the point where you have a 1/2, okay, it's 1/2 comma root 3 over 2, happens at what angle? And that would be at pi over 3. All right, so at pi over 3, we have 1/2 comma root 3 over 2, which of course is 60 degrees, pi over 3 radians. All right, if you take 60 degrees away from 360, that would give us its reference angle in the fourth quadrant of 300 degrees. 300 degrees, when I want to convert that to, in terms of pi to radian measure, would be, well, pi over 3 is 60. And so how many 60s do I need? I need 5 pi over 3. So 5 times 60 gives me that 300 degrees. All right, so I can now say that x cosine of what angles? Cosine of pi over 3 and cosine of 5 pi over 3, in fact, give me x value of 1/2, which is when the derivative is equal to 0. So those are my two critical values on my number line. Okay, so I go ahead and make my number line and make sure that I put pi over 3 and 5 pi over 3 on my number line. Of course, I have f and f prime, and these are both zeros. All right, so now I need to test values to the left of, and I also want to go ahead and put on there the 0 and the 2 pi, because that's as far as we are going. All right, so those are my brackets. That's as far as I'm going. I'm not going any further than that. All right, so I can go ahead and test. I need to test a value between 0 and pi over 3, between pi over 3 and 5 pi over 3, and between 5 pi over 3 and 2 pi to see what's happening. All right, so if you want to pick a value between 0 and pi over 3, I could pick pi over 6 or pick pi over 4. It doesn't matter. One of those two would probably be what I would recommend. And so I'll go ahead and just pick the pi over 6, because I know it's the exact opposite points as this, so root 3 over 2, 1/2. All right, so again, remember I'm plugging it back into f prime of x. And so it's 1/2 minus cosine of, I said I was picking pi over 6. So cosine of pi over 6 is root 3 over 2. Okay, so I'm looking at 1/2 minus the square root 3 over 2. So radical 3 over 2 is larger than 1/2. And so, in fact, I'm going to go ahead and say that this would be negative between 0 and radical 3. All right, between 0 and pi over 3. Then I need to pick a value between pi over 3 and, so between pi over 3 and between 5 pi over 3. So I'm definitely going to go ahead and pick one of these that are on the, one of my quadrantal angles. So I'll just go ahead and pick pi. All right, so what happens at pi? The point at pi would be -1, 0. And so if I go ahead and test in, and of course my cosine is the -1. So 1/2 minus -1 would be positive, and so we know that this is going to be positive, all in that range, in that area. Lastly, I need to pick a angle between 5 pi over 3 and 2 pi, so of course that's between 300 degrees and 360. So if I pick 330 degrees, okay, that would be right here, so 330 degrees, which of course would be the point negative root 3 over 2. The root 3 over 2 negative 1/2. And so still the cosine of 330 degrees would be the same as the cosine of 30 degrees, which we already did. So 1/2 minus root 3 over 2 is still going to be a negative value in that range. All right, so now we're ready to go ahead and make our conclusions about what f looks like at that point at each of these intervals. So we can see here where f prime was negative, we would have a decreasing function. Here, between 60 degrees and 300 degrees, we'd have an increasing function, and then again decreasing between 300 and 360 degrees. Okay, so then some conclusions that we could make would be that f is decreasing. We'll go with decreasing first. From 0, remember we start at 0, okay, from 0 to pi over 3, and also from 5 pi over 3 to 2 pi. And of course that's because f prime is less than 0. Okay, f is increasing between pi over 3 and 5 pi over 3. And of course that's because the derivative is positive. All right, and then you can take a look at relative mins and maxes, and we should be able to see that we're going down to a min, back up to a max, and then down again. All right, and then the graph stops, of course, at 2 pi. And so we would say that we have a relative min at x equals pi over 3 and relative max at 5 pi over 3. And again, the reason would be because the derivative changes from negative to positive for the relative min and from positive to negative for the relative max. All right, guys, I think that's enough for today. Thank you so much, and be ready for class tomorrow.